Okay, so one question is, why do we learn computation? Is it advantageous or is it just for fun? Or okay, of course it is for fun, but it's also very useful right now for advanced research or even basic work. We need computing right now. So just to tell you that you may be doing other courses like classical mechanics, electronics, or mechanics. So you can use plotting, some solving differential equation. Earlier, we used to do this analytical computation only. No, so hydrogen atom, we do solve analytically. Now we can also solve it on a computer, and we can look at the results. Okay, so I would say strongly recommend that once you learn few things like plotting, solving equations, you should use it, and that's where you also kind of learn the syntax, keep remembering the syntax, and it makes you even better, and you can connect things. And okay, anyway, so for advanced research, we should keep in mind that the problems at present in science and engineering both are quite complex, and so present available analytical tools don't work. Most of the tools developed are for linear problems, like linear PDs, linear ODs, linear algebra. So they don't work for nonlinear problems. So then we need to, well, basically, what are the problems we have solved? Linear oscillator, simple harmonic oscillator, which is linear problem, and hydrogen atom. Solved both in classical mechanics and quantum mechanics. Okay, so in physics, you may know this, or every student would have fair idea about these two problems. But beyond it, we have simply no analytical solution. So for helium atom, there is no analytical solution. Okay, as soon as you put nonlinear oscillations, then there is no analytical solution. So the idea is that you go for either mathematical tools like perturbative methods. In quantum mechanics, you've seen that there's a perturbative methods. Classical mechanics too has this method, but normally we don't cover it in courses now. One reason why we don't cover it, because computations have become very easy, in the sense because computers are available, they are good programming languages, you can do things very easily. So why do extremely complicated math? You can simply get the result by solving those equations. Okay, so this is one reason. I mean, okay, so this is also for simple things as well as for complex things. Like I want to understand large molecules, then I use computational methods. Now, so computer simulations are like numerical experiments. So it is basically experiment, and you need to do more work for making models. So understanding is not coming from computer. Huh? So please keep in mind that computers are only helping us solve those equations. But to understand, you need to understand the solution. You need to understand the data, understand the plot. So computer can plot it, but then you have to see what those plot means. So it's like experiment. So I'm going to say a little bit more a little bit later. So we made models based on numerical results. Often simulations or computer experiments complement the real experiments. So the example I can give you is we can work with liquid metals. Okay, so liquid metals like mercury or molten iron. Okay, so for example, in car industry, we work with molten materials. So you can do experiments with them. I mean, apply magnetic field to see the flow, or what happens to the flow. At what temperature it starts boiling. That's one. But if you want to look at the flow profile, metals, we can't really see through lasers, because the laser cannot go through the metals. It can go through air and water, but not through metals. then simulations becomes very handy. Okay, we can do experiments on parts of the atmosphere, not all of atmosphere. So for all of atmosphere, if you want to do it, then we need computer simulations. Sometimes even for like a given system like rainwater formation, we complement both experiments and simulation. So we need to do both. Okay. So also computers give very it gives you an avenue for visualization. Now we can do 3D visualization. So it's really very nice to be able to see what the data is telling us. So this is why we need to do both real experiment as well as computer experiments. And computers have become very powerful. At present, we can really simulate very, very complex physical phenomena or biological phenomena. So many unsolved problems are being solved using computers right now. So some examples which I gave you is I'm giving right now is turbulence and computational astrophysics. Okay, there are many, many more. I mean, in biology there are tons of them. In engineering also. So there are huge amount of things which remain unsolved, which we are able to solve now using computers. So just let's go through applications in physics. Okay, I mean there are much more than what I'm going to show you in the slides, but it'll give you a fair idea where computers are heavily used. So flows, which is something which I work on. So flow all around us, no? Fluid flows, astrophysical flows. So weather and climate forecast. This is one place where without computers we can't do anything. So that's one. You understand, no? When you simulate the whole weather system and forecast for rain, temperature. Climate forecast is for 100 years and so on. Now, flow around automobiles, aeroplanes, space vehicles, rockets. Oil exploration. So you're looking for oil inside the earth, but you simulate. Of course, you can get some data from within the earth, but there's a lot of simulations are done. Physics of turbulence. We can simulate turbulent flows. Flows in and around stars, black holes, galaxies, planets. Yeah, so in astrophysics is heavily used. Quantum turbulence is one interesting example where in quantum systems there is turbulence. Like superfluid is an example where you see turbulence. So that comes under quantum turbulence. So I will not get into that. Well, there's one example which I'm going to give you when I cover Schrodinger equation, but people are using computers for solving these systems. Now, materials and quantum systems. So all kinds of materials, be it polymers, large molecules, or strong materials. Like for aeroplanes, we want strong and light materials. Okay, drugs, we want medicines. So for these, the tool used is the density functional theory often, and also quantum Monte Carlo. Okay, so these are tools. We will not cover it in this course, but you may be hearing these words. So these are the tools which are used for simulating quantum systems or understanding quantum systems. So they give you idea about what is the stable structure among the molecules, what is the energy levels of the molecule, how the molecules interact with each other. All that is done using this. Now, nonlinear physics in health. So here also the nonlinear physics flows is an important thing. Also in health, like blood flow is an important problem. In heart, how the blood is flowing. Epidemic evolution for in COVID times, it is very critical. Drug design, understanding the brain. So there are projects now going on in universities where people are trying to simulate full 10 power 11 neurons, okay, and how they are firing, and they're trying to process images, memory. Memory is a big problem in brain. How do you remember things? Image processing. So all that is being done right now. So social network, everybody is aware of. Computer networks, biological networks. So this is an important topic of research. Human body, like as I said, would heart, digestive system. You can simulate them, and you can get some insights. Earthquake. This is one more place where there's one challenge: how to predict earthquakes. Okay, and there are work going on in that direction. Now, machine learning has become very important area of research at present. So we will not do machine learning in our course, but examples are, everybody knows about it now, self-driving cars. These are using machine learning. So it basically, it collects data while driving, then it learns and it becomes better and better drivers. E-marketing, like Amazon is using shopping pattern and then trying for advertising, their inventory management and so on. Google Translation. So right now the captions in YouTube for any movie if you see, so all they are automatic from speech to text. That's machine learning. French to English or vice versa. So that's all based on machine learning. So it's well, this would be N here. I missed. So machine learning is a big thing in science and engineering. Now defense is important. You can see it for aircraft designs, image processing, terrain mapping, and so on. Economics, of course, banking, stock market. Okay. Complex physics, again, so flows is something which I wanted to say. They are complex anyway. What are other complex systems? In universe, you see dark matter, dark energy, universe. Fusion is one more example. But I mean, all complex things which we don't understand is called complex physics. Like brain is a complex system. Okay. Fusion is a colliding of two nuclei and they fuse and they generate energy. So that's why the fusion is important. So in nuclei, so the simulated using lattice quantum chromodynamics, lattice QCD. Okay. So these are all being worked out in computers. So in particle physics, it's accelerator simulations. So basically, you collect all the data, analyze it. So when any scattering of two particles, it generates huge amount of data. And we need to use computers for analyzing the data. It's all automated. So now, so you may ask, what is the relationship between theory, experiment, and computation? N is missing here. So this is a cycle. So we observe certain physical observation. So observation could be by experiment or by looking at by naked eye, or a telescope. So experiment doesn't mean that you do it in your lab. Experiment could also be just observing a phenomena. In astrophysics, we normally don't do an experiment, but you observe. In biology also, you basically observe things or do computer simulation. So you can also do computer simulation and observe how things are evolving. Okay, that's another experiment. Now, given the observation, you construct a theory that explains the observation, okay, and make a prediction. So it makes a prediction. Okay. So for example, Newton's laws, it made predictions about the orbital motion of the planets, how the planets, I mean, there are some three-body interaction, tidal motion, all these are predictions, and they were found to be reasonably good with the observation. So prediction and observations go hand in hand, and that's how we validate a theory. So there must be predictability in a theory. So once you predict, then you validate it. Okay. If the experimental result and predictions match, then theory is good. Otherwise, you make a new model. Okay. This model is no good. It doesn't explain the observation, all the observation. So you make another model. So we go on like this, and you try to better the model. But sometimes the model was good for 100 years, but then suddenly some observations come, either by experiment or now computer simulation. And it turns out that this theory is not able to explain the observations. So it happened for Newton's laws, Newton's framework of mechanics. So Einstein's new relativity came, or quantum mechanics came. So these new things came because those models were not good enough to explain the observation. So some examples I can give you. So superconductor is where experiments were there. It happened many years back, last century, early last century. So here experiment was dominant. Now, of course, simulations are done for new superconductors. Aeroplane is the place where both experiment and simulations are roughly 50-50. Okay, there are some simulation, there's some experiments. Weather and universe is essentially more simulations. Okay, so you can see that which part is dominated by numerical simulations. There are theories, but I mean, we need to do much more than, well, theories are not powerful enough to capture the observations. There are, I mean, as I said, there are theory for stars, but they're not good enough. They can't explain the magnetic field, or they cannot explain the various phenomena we observe on X-ray emission and so on. Okay, so we need to simulate. There's no other option. Theories are very limited. They have very limited predictions. Now, so there's new thing called data science now, right? I mean, machine learning is part of data science. So what's the difference between computation and data science? Though we are focusing on computation in this course, but we should know the difference. So computer science is simulate and forecast based on underlying physical principles. So one example is I predict occurrence of rain. So that rain occurrence can be done by simulating the velocity field, humidity, temperature, and making a forecast. Now, but you start with physical principle. Now, in data science, the idea is that you use the data to make a forecast. So you collect 100 years of data of temperature, humidity, wind patterns, and see whether it led to rain and not rain. And from that pattern of the data, you see whether tomorrow there will be rain. So that is basically data, not much, well, basically you don't worry too much about physical principles. Just based on data, I made a model. So this is done for fog prediction, rainfall predictions. So both these things are being used. Now, data science is being heavily employed for science as well as for business. E-marketing is like Amazon, Google, they are using heavily by seeing my search pattern, marketing pattern, a shopping pattern. They give advertising, yeah, so e-marketing is hugely using machine learning. So that's based on data.